Right. So, so this is a small session. So I want to do one thing, that is do a little bit about linear programming and integer programming. Actually, we are going to completely finish the syllabus. Okay, I thought of doing only part of the syllabus, but because you guys are interested, especially, I thought of fully doing it. And today we want to finish it. Okay. Anyway, we have already done the two past papers, but you never know, right? I told you that the last two past papers, the question is on the graphical method of linear programming. But there's another approach for linear programming, a simplex method, and also there's a subset of linear programming called integer programming. So we are going to finish that, okay? But no past paper questions, nothing, just theory part and some examples, okay? Right, so let me open the note. Right, so remember, linear programming is optimization. You have objective function, right? We have objective function, and then we have set of uh, constraints or restrictions, right? So there are two ways you can solve it: graphical method and simplex method. So last time we discussed the graphical method. Okay, let me open my pen. Right. So do you have any questions on graphical method? Are you really comfortable with graphical method? Right. So what is the idea behind graphical method? Uh, you just plot the constraints as a equation, not as a inequality. You just draw the lines and then mark the regions depending on whether it's less than or greater than. Then the enclosing area is the feasible area, right? Enclosing area is the feasible area, and additionally you can use that your variables are bigger than zero also as another constraint. Okay. When we use the fundamental theorem of linear programming, because your optimization, your objective form is something like this, right? Something like this, 2x minus 1. So your task is find which point you get the maximum value. Always the maximum value is one of these corners, and you just find these corner values and then substitute those corner values. Of course, how to find the corner values? Simultaneously solving. Then substitute each and every value in the objective function and find what is the biggest, and that is the optimum solution. And the optimal solution is always one of the corner points. So that is why we first need to find the corner points. Okay, so that is graphical method. That is a graphical method. Okay. Right. So that we discuss. That we discuss. So today I first want to discuss the second approach. Graphical method, you can do it, but you need either, it must be either two variable, or you need some tools to draw the graphs, right? It's not very easy. It's very easy. That is the easiest way, but when you have just few variables. But when you have more variables, because then three variables means planes, three-dimensional. So it's not very convenient. So for simple things, yes. But when we have more and more variables, it is not the easiest. Okay. So that is why we have simplex method. Simplex method is complex approach. So therefore, for simple things, you will find that simplex method is unnecessarily complicated. But the good news is simplex method is very systematic approach. Even though you have 10 variables, right? 4 variable, 5 variable, 6 variable, we can easily apply. And also we can write a software or program automating it. Okay. Because it's not a graphical approach. Right. So at first you will find it little bit challenging or right intimidating. But once you understand it, it's very easy. Okay. Only thing is it has bit of steps. Right. So far in the exams, they have never ever asked you to solve a question using simplex method. I hope that will continue. But in case they ask, so you must be prepared. Maybe they can ask a very simple question using asking you to solve using simplex. Okay. Right. So simplex method is an algorithm to solve linear programming problems, just like the graphical method. It systematically checks the vertices of the feasible region to find the optimal solution. Actually, we are also indirectly checking those vertices or the intersection points. But this is more matrix-like approach. We are doing the same thing, but in a matrix mindset. So these are the steps, right? 8 steps. Okay, 8 steps. So that is why I told you that sometimes you get intimidated seeing that, okay, it's a 8-step big problem. No, it's not that hard once you understand. So step number 1 is set up your problem. That is write your objective function and the inequalities. That is obviously we need to do, right? That is, you just write down your objective function and inequalities, constraints. Step 2, anyway, we have done it. We already did that for the graphical methods also. Convert the inequalities into equations. But when you do this, you can't just, for example, x1 plus x2 less than 2. You can't simply say x1 plus x2 is equal to. This is what we did in graphical method, so that we can draw this line. But here, you must say that x1 plus x2 plus some slack variable equal to. That slack variable we want to find out later. Because this inequality, we say that for this, if you add another constant, it will be equal to 2 because now it is less. So that is how you convert your inequalities into equations. Okay. Each equation, for each equation, you need one slack variable. For another inequality, you need another slack variable. So that you can call them S1, S2, and so on. Slack means Aduapurona variable. Right. So then construct the initial simplex tableau. It's like table. Right. Write the objective function as the bottom row. So first you write the constraint, then the objective function, but with these slack variables now, because now these are equations. Don't worry, we will do example, right? So then the 4th step, the most negative entry in the bottom row identifies the pivot column. So now it's, you think it like a matrix, okay? So then you calculate the quotients, then perform the pivoting to make all the other entries in the column 0. Then when there are no more negative entries in the bottom row, we have finished. Otherwise, we should start again from step 4 and continue. Step 4, 5, 6 is a loop. And finally, when you are running out of negative values in the bottom row, we are done. Now you can calculate or now you have the answers in your table. Okay, right. So don't worry too much about this description, right? That is, I just gave it for the formality. Let's do it one question, okay? So this is, I have shared you these are directly taken from YouTube also. I have given you the recording so that you can, if you need more details, refer to the recordings, relevant video, okay? Right. So the first one is already we have discussed, that is related to the this is related to the graphical method. Okay. This is related to graphical method. This is basically the example I am right now doing, and this is the second example. Okay. Right. So let's quickly do it. So this is our problem. Suppose a company manufactures different electronic components for a computer. Components A require 2 hours of fabrication and 1 hour of assembly. say fabrication time, let's say X, 2 hours. So the idea is how many components you want to manufacture to maximize your profit. Right? So you have the flexibility to decide how many A components, how many B components you want to manufacture. Right? So A require 2 hours of fabrication time and 1 hour of assembly time. Component B require 3 hours of fabrication time and 1 hour of assembly time. And component C require 2 hours of fabrication time and 2 hours of assembly time. The company has up to 1,000 labor hours, right, for fabrication and up to 800 labor hours for assembly each week. So you need to calculate this per week basis. If the profit on each component is A, B, and C, that is $7. Each A component gives you $7 profit. B component give you $8 profit. C component, each unit has $10 profit. How many of each should be produced to maximize the profit? Okay, so don't think that you only produce highest profit items because it opposite. Though you get the highest profit, it will use up your resources. Okay, right. So that that is why we have this problem. Right. So that is your question. Now you want to put it into. Uh, now we want to put it into uh, variables, right? So these are maximization. Uh, so let's assume x1 number of A components, x2 number of B component, and x3 number of C component, or you can say x, y, z, or A, B, C. Okay. So then our profit formula is, because every unit of A gets 7 profit, 7 unit profit, 7 into x1, because we are going to produce x1 number of A components. These are independent components. So because we are going to produce x2 number of B components, our total profit is 8 into x2. And for C component, our profit is 10 into x3. Okay, 10 into x3. Right. So let me fix there's a space issue. Right. It's not a bug, it's just a space. Okay. Right. So that is how now we want to maximize this. We want to find the maximum P. Then the constraints are 2x1 plus 3x2, because this is number of labor hours for uh, fabrication and labor hours for assembly. So 2 into x1 plus 3 into x2. Okay. Plus can you explain the question again? Okay, let me explain it again. Okay. Right. So the question is this. This is same as the question we did last time. Okay, similar to that. So we can either produce, say, component A means product A, product B, or product C. Right. So we have the flexibility. You are a manufacturer. Right. You are a manufacturer. You can either produce product A, product B, or product C, or any mixture of those. But you have constraints. What are those constraints? For product A, you need, for each unit of product A, you need 2 hours of fabrication. For fabrication, you need 2 hours for one unit of product A, and 1 hour is needed for assembly. Okay. For product B, 3 hours for fabrication and 1 hour for assembly. For product 3, you need 2 hours for the fabrication and 2 hours for assembly. Okay. So that is how this formula is there. Now, if you build x1, x2, x3 number of product A, product B, product C, right? So that means if you take the fabrication time, right, x1 into 2, because you would build x1 number of A components, you need 2 hours of fabrication. That is x1 into 2 is fabrication hours for product A, because we are going to create x1. For product B, you need 3 hours, 3x2, x2 number of components, each component 3 hours. I'm looking at the fabrication. Then for product 3, 2 hours of fabrication, we are going to have x3 number of those. And remember, there's a constraint. The total number of fabrication hours we have is 1000. So therefore, this must be less than or equal to 1000. So then we'll take the assembly hours. Remember, we are going to have x1 number of component A, x2 number of component B, and x3 number of component C. For component A, you need 1 hour of assembly. So therefore, 1 into x1. Component B, you need again 1 hour of assembly. So therefore, 1 times x2. For product 3, you need 2 hours for assembly. So that is 2 times x3. And total number of assembly hours available is 800, right? Therefore, this must be less than 800. So those are the constraints we are having. And the optimization function is each unit give you A give you $7. We are going to have x1 number of A component, x2 number of B component, x3 number of C component. From each unit of A, you get $7. 7x1 is the total profit. 8x2 is the total profit for B component. 10x3 is the total profit for C component. And this is my profit function. We want to maximize this. So this is our objective function. We want to maximize this. And these are the two constraints. Other than that, additional constraints are x1 is greater than or equal to 0, x2 is greater than or equal to 0, x3 is greater than or equal to 0, because those are number of components. You can't build negative number of components. Is it clear now? Or do you want me to explain it further? So that is how you get these, right? The two constraints, additional constraint, these are all 0, and this is my profit function. Okay, so we assume that we are going to build x1 number of A, x2 number of B components, because those are independent. Actually, component is not a very good word. We should have in products. Okay, products. Right. So that is step number 1. You present the story into a mathematical notation. So now we want to introduce those slack variables, because we want to convert these inequalities into equations. How to convert it into equations? For each and every inequality, you introduce slack variable, but don't consider these things. Those. Okay, so here, the profit one, you don't need a slack variable, because it's already an equation. Profit equal this, so you don't need a slack variable for that. It's not inequality. But you write it like this. You take everything into the P side. So therefore, P minus 7, this goes to the other side. Minus 7x1 minus 8x2 minus 10x3 plus P equals 0. So that is very important. You take all the variables into the profit side and write it as a equal 0 equation. And other inequalities, you need to introduce slack variable. So this says this must be less than 1000. Then you can say 2x1 plus 3x2 plus 2x3 plus S1 equal 1000. When you add this amount, which is a positive amount, it must be equal to 1000. It's a newly introduced variable. Other than now x1, x2, x3, now we have another variable, right? Which we don't know what is the value. So this one also we convert to equation 1x1 plus 1x2 plus 2x3 plus S3. Oh, actually I should have called it S2 equal 800. I think it's my typing mistake again. Yeah, so this should be S2. Okay, I will give you the updated note, because I just prepared it today only. Not today, I think I prepared this yesterday. Right. So this should be S2, okay? Right. So that is, those are additional variables we introduced to make these inequalities equation. So here it's already equation, but we took everything into the P side because we are going to put it into a matrix format. So now we are done with step number 2. Step number 3 is construct the initial simplex table. Okay. Now you want to convert this into a table or sort of a matrix. Okay, sort of a matrix. But let's call it a table. Okay. Right. Now you can see I have not done anything else. Rather, just I have taken those into a table. X1, X2, X3, S1, S2, P. Right. So the first one is X1 is -7, -8, -10. P is 1. This part is 0. S1 and S2 are 0. Okay. 2, 3, 2. You can see. 2, 3, 2. This is 0. This is 1. And this is 0. 2, 3, 2, 0, 1, 0, 1000. 2, 3, 2, 0. Sorry. 2, 3, 2, 1, 1, 0 because I have taken the profit to the right last one. Right. 2, 3, 2. 2, 3, 2. S1 is 1. S1 is 1. No S2. No P value because this inequality has just no S2 or P value. Then second one. 1, 1, 2. 1, 1, 2. Then no S1 value, but S2 value is there, no P value. Actually, this column is not required. Actually, I thought of removing this column. Maybe I will give you a new version of the note without this P column. For the time being, forget about this P column. Actually, you don't need this P column, okay? Okay. So then the constant here, 1800. 1800. That is from here and here. Okay. And finally, you write down the objective function. Objective function. So there x1 is -7, x2 is -8, x3 is -10. So for -7, -8, -10. Okay. No S1 value, no S2 value, but P value is 1. Right? P value is 1, 1P. Its coefficient. And this constant is 0. Constant is 0. Okay. So don't look at this one for the time being. Just look at this table. That's it, right? Nothing fancy. Nothing fancy. So now we have converted into a table. Forget about this pivot and those things for the time being, okay? Right. So now we have put it into a table. Just the equations are now in a table or matrix format. So these are our introduction of S1 and S2. Because we had two inequalities, we need to introduce S1 and S2. This is how, actually you can forget about this column also. You don't need that column. Okay. Actually, I will remove this column and re-upload it. Okay. So then it's very easy. Okay. Right. So now we are into the step number. Now we are going to go into loop now. There, what our task is find the pivot column, then pivot value, and then convert the pivot value into 1, all the other values into 0. Right? So then you repeat that as long as you have negative values in the optimization field. Okay. Okay. So simple as that. Okay. Right. So what is my task now? Look at the optimization formula. That is your final one. See whether are there any negative values. In this case, 3 negative values. Out of these values, find the most negative value. That is your first pivot column. In this case, -7, -8, -10. The most negative value is -10. So therefore, this is your pivot column. Okay. So now we have identified the pivot column. Then we need to identify the pivot value. Pivot value is one of the value in that column. How to find the pivot value? Pivot value must be one of the value from your inequalities. So this is how you do it. Now you have this value, right? Right hand value. Divide the right hand value by the corresponding variable value. Now my pivot column is x3. Its value is 2. 1000 divided by 2 is 500. This one 800. 800 divided by 2, because this is also 2, is 400. Now look at what is the smaller value. Smaller value is 400, and that is your pivot value. Now I have first figured out the pivot column, most negative value in the last field. Then I have figured out the pivot value by dividing your constant in the right hand side by the pivot coefficient and selecting the smaller value. Now I have identified the pivot column and pivot value. Okay. Now your next task is using elementary row operations. Now you can consider this as a matrix. Okay, matrix. Right. Using elementary row operation, convert this into one. Right. First. Then using elementary row operations, convert the other columns, other values in that row, including the profit maximization value, convert them into zeros, but use elementary operations. So then you go to the next negative, biggest negative value, and again divide those values by its coefficients, find the smaller value, and that will be your pivot value. And then again convert it to 1, convert others into 0. You do this until all your negative values have taken care of. Then you are done. Then you can say what is the optimized value. And for optimized value, what are the x1, x2, and those values are. Okay. Right. So let's do it for the, now we are in the first iteration. Now we have identified the pivot column because this is the most negative value. Then we have divided our value from the coefficient and found the smallest value, quotient. So therefore now we have found the pivot column and pivot value. Okay. Right. Any questions? So now we are in this step. Okay. Now we are in this step. It's the same thing here also. Okay. Same thing. Right. So now your task is, because this is my pivot. If there's a tie, you can select any of. Okay. Any of those. Right. This is not a tie. 400 is smaller. Now you want to convert this into 1. So it's very easy. You just remember what are the elementary row operations. Any row can be multiplied by constant fraction of more than 1. Okay. Then row can be, say, rk equal rk plus constant time rj or kl, or rk equal k times rk plus rl. And also you can swap rows, but here you don't need to do that because it doesn't make any sense. Only you need to use either multiply a row by a constant or add one row with another row, but any row you can multiply by a constant while you are doing that, or you just take your constant as 1. So therefore, how to make it 1? You just multiply this row by half. Then 1 become half, 1 become half, 2 become 1, 0 is still 0, 1 become half, 0 is 0, 800 become 400. So this is a temporary column. Once you find the pivot value, you forget about that, right? But this is, you keep continuing. Now we have make it 1. Right? So now our next task is convert these into zeros by using elementary row operations. Right? Elementary row operation. So how to do it? How to convert this into 0? So this plus, or half of this plus, sorry, minus half of this plus this. Minus half into 2 is -1, -1 plus 1 is 0. But make sure you do it for the entire thing. Or you multiply this by 2, -2, and add it to here. Both will work. Either you multiply this by half and minus half and add it to this, then -1 plus 1 becomes 0, but make sure you do it all. or to this, right? That is, let's call this row 1, or you can say row 1 is row 1 plus minus 2 times row 2, because then minus 2 plus 2 is 0. But make sure you do it for each and every column. This one, either you multiply this by 5 and net, or you divide this by 5 and net, whatever. Okay. Right. Here we have used R1 is minus 2 times, R1 is minus 2 times, R1 is R1 plus minus 2 times R2, so that R2 and minus 2 become 0. But you need to do the same thing, right? This is minus 2 into half is minus 1. Uh, R1 is minus 2 times R1, so that means 2 minus 2 times half. It is 2 minus 1, which is 1. This is 3 minus 2 times, right? Minus 2 times half. That is 3 minus 1, which is 2, right? Which is 2, and so on. Here also you need to do the same thing. That is, R1 is 1000 minus 2 times R2 minus 800. 1000 minus 800 is 200. So now this has become 0. So doing this row elementary operation, right? Because then 10 and minus 10 becomes 0. Okay. You are doing it to the R3. Here R1, R2, R3. Okay. Then we have made this 0. Now our iteration 1 is done. We have made the pivot value 1, other value 0. Now you need to do this 2 times again, because we have another 3 negative numbers. So then take the next most negative number. You can't go to any negative number. This is the biggest negative number. That is why we did it for that. Then next biggest negative number is this one. That is your next column, pivot column. Then divide these values by this value. 200 by 2. 400 by half means 400 into 2, 800. This is 100. This is 800 then. Right. So let's move on to that step. Before that, once you finish your first iteration, right? So you need to do one more thing. That is, remember, this is our pivot value, right? This is our pivot column. You need to swap. Now remember, when we start with S1, S2, and P. Why S1? Because this is the first inequality. To make it equation, we add S1. This is our second inequality. To make it equation, we added S2. This is our profit maximization. So therefore, it is P. Okay. Now I ask you to forget about this, right? So I will remove this column and reshare. Now, once you are done with this, this is your pivot column and this is your pivot value. Now, pivot value corresponds S2 and this is X3. You need to replace your S2 with X3 after doing this. Okay. So that is a very important step. Otherwise, you will forget it. Now, therefore, in the next one, you will see identical table, but this is X3. This is X3. I have explained everything. Now we are fully done with the iteration 1. Now only you go to the looking for the next most biggest negative number, which is minus 3. Okay, minus 3. Then you divide 400 by half, 200 by 2. Then the smallest is 100. So therefore, this is your new pivot for the second iteration. Now your task is using elementary operation, make it 1. Using elementary operation, make these zeros. How to make it 1? Multiply this row 1 by half. Right? Multiply row 1 by half. Right? So this is the same table. So now you got this. Now you want to make these zeros. Right? Again, do elementary operations. Right? How to make it 0? Maybe multiply this by minus half and add it to this. That is, R2 is R2 plus minus half times R1. Okay. That will make this 0. But you make sure you do it to the entire row. Okay. And how to make this 0, right? multiply this by plus 3 and add it to this. Then plus 3 prime minus 3 is 0. But make sure you do it to each and every column. So then you will end up with this table. Remember, you need to do it for each and every column. Okay, your row operation. So now we are done with the second iteration. After, now remember, this times our pivot is this, because that was the low value we had, right? So therefore, after making this 1 and making these zeros, you replace this variable, which is S1 originally, with this variable, because we are done with second iteration. Once you do the iteration, you need to replace this variable with the relevant slack variable. Now it is x2, x3p. Earlier it was S1. And here also earlier S2, but after first iteration we made it x3 because we did the third column. Right. So now that is the end of the iteration 2. Now this x2, x3. Now you have another negative value, that is minus half. Okay, so therefore obviously that is my third pivot column. Then again divide this by your coefficient. 100 by half, 350 by 1/4. So there the smaller value is 200. So therefore this will be the pivot value for this. Then again you make this 1 by multiply by 2, right? And then make the 0 by elementary row operations. So this after multiply by 2 you get this. Right? Make a temporary column එක මේක ඊට පස්සේ අමතක කරන්න. මම වැඩ කරන්නේ මේකත් එක්ක. මෙන්න මේ column එක මකලා දානවා මම. මේක ඕනේ නැහැ ඇත්තට. ඒකට වැඩි තවත් පොඩි ඕක. මම ඕක මකලා ආයෙ අප්ලෝඩ් කරනවා. Right. So then using elementary operations you want to make these 0. හරි මෙයා ඍණ 4 එකකින් වැඩි කරලා මෙයාට එකතු කරන්න. එතකොට මෙයා බිඳුව වෙනවා. මෙයා ධන භාගයෙන් වැඩි කරලා මෙයාට එකතු කරන්න. එතකොට මෙයා බිඳුව වෙනවා. එතකොට මේ කරන වැඩි අනිත් කොලම් වලට කරන්න. Now we need to swap, because this is my pivot column's pivot value. So therefore now you need to swap this and this. Earlier it was x2. Now you replace that value, whatever the current value, with this value. Right? And now we are fully complete done. දැන් අපේ වැඩේ ඉවරයි. Simplex method එක implement කරලා ඉවරයි. මේක කරන්න පුළුවන් වඩ විනාඩි 10ක් ඇතුළත. හරි? and the exam එක දෙන්නත් ඉඩ තියෙනවා. Okay. Right. So therefore this is our final result. මේ තියෙන මේකම තමයි අලුතෙන් මුකුත් නැහැ. මේක උටයි මෙන්න මේ p column එක අමතක කරන්න. Sorry, not this. Right. This is our final one. Forget about this. Now we are done. Now we are done. So therefore this is the optimum profit, which is 4,400. Okay. And when you get that profit, optimum profit, your x1 value is 200. When you get that optimum profit, your x3 value is 300. And your x2 value is not here. If it is not there, it is 0. That means you don't build x2 component. Okay. And also, right, because your s1, s2 is also not here. Right? If a variable is not here, that means those are 0. You can see here we have only x1, x3. x1, x3 and the profit. The other values are 0. So then someone will ask, what is mean by other values are zeros? Of course, now this is your maximum profit. You get the maximum profit if you make 200 x1 components and 300, A components, 300 B components, and C component, x3 is C, and 0 B components, because x2 is 0. x2 is 0, how do you know? Because x2 is not here. Okay. So then what is mean by S1 and S2 is 0? S1 and S2 is 0 means your slack key is 0. That means you have totally used up your assembly time, right, and fabrication time. Sometimes in the simplex method, you may ended up with some S1 or something here. say S1 is 5. That means after doing this, you have 5 labor hours remaining. You can't use it. ඒක ඔයාලට use කරන්න විදියක් නැහැ. මොකද ඔයාගේ product වලට ඒක හරියට බෙදලා ගියේ නැහැ. ඒකට කරන්න දෙයක් නැහැ. හරි. Because we are interested in maximizing this. මිනිස්සුගේ labor hours ඉතුරුනාට කමන්නේ නැහැ. Profit වැඩි වෙලා. කාටද කියන්නපති ඒකත් දාලා අපිට profit එහෙම වැඩි කරන්න බෑ. මොකද ඒ component එකට දාන්න තරම් එතන labor hours මදි. බෙදිලා නැහැ. Okay. So that therefore it's very important that you know how to interpret also. Okay. So we are going to get optimum profit of 4,400. If you make 200 number of A components, 300 number of C component because this is X3, and 0 number of B components. ඒ කියන්නේ B එකක්වත් හදන්නේ නැහැ. B හදන්න ගියාම වැඩි profit අඩු වෙනවා. And S1 and S2 is not there means you are going to use up your assembly time and fabrication time 100%. No one is going to idle for the week. Okay. Right. Any question? Any question? Okay. Right. So this is an easier question. Actually, I generated this by using ChatGPT. I asked ChatGPT to give me a simple example to demonstrate simplex method. So this is the one ChatGPT came up, and I just put it into the your slide. Okay, and the good news is it has only 2 variables. Now here you can't go for the, of course you can go for the graphical method, but when you have 3 variables, it's a plane, 3 dimension. So this is not easy thing to solve using graphical method. But of course, this one you can solve using graphical method also because you have only 2 variables, right? Unless they say, examiner says, use simplex method, use the graphical method. But for 3 variables, you have no other option but to go for simplex method. Okay. Whether examiner says like that or not, because how do you draw 3-dimensional things in the exam time? Okay. You don't get any online tools. Right. Anyway, this can be done using graphical method also. As exercise, you do this using graphical method also, right? And see whether the 2 answers are correct. So now we are using simplex method. So in the exam, they can give you something like this, like a simple question and ask you to specifically ask you to use simplex method. Then if you use graphical method, you will not get marks, maybe 0 marks. Right. So how do you do this? First, introduce the slack variable for this and this, and take all these variables to the left hand side. Okay. So this is the result. So this is our question, and this is, we have taken all these into the z side and equal 0. For this one, I have introduced S1. For this inequality, I have introduced S2. Slack 1, slack 2. Okay. And now you want to convert this into table. So this is the table. Okay. This is the table. Then you need to find which one has the most negative value. Now this one is easy because we have only 2 negative values. So that means you need only 2 iterations. So then divide your values by these coefficients. 6 divided by 2 is 3. 12 divided by 2 is 6. So smaller value is 3. So therefore this is your pivot. Now you using it in elementary operation, make this one, make these zeros. So this is divide by half or divide by 2. Now you have make it 1. Now you can make this 0 by multiply this by -2 and add it to this. Right? You can make this 0 by multiply this by 5 and add it to this. Simple as that. Right? So now you have not finished your iteration 1. And now you need to replace, because this is your pivot, you replace S1 with X2. S1 with S2. Then you are done with the iteration 1. Okay. Iteration 1. Now you have another negative value. Right. Again, divide your Z values. Sorry, is it not Z values? Your constant with 3 divided by half, 6 divided by 2. Smaller value is 3. So therefore, this is your pivot. Then convert this into 1 by dividing this, multiplying this by half. Then elementary row operations make these two 0. This is first we make it 1. Then of course we want to make this 0. That is uh, divide this by -2 and add it to this, or multiply this by -2 and add it to this. Okay. Then divide this by 2 and add it to this. Sorry, -2 and add it to this to make R3 also 0. Because no, you don't need -1 because already minus is there. Divide this by R3 is R3 plus R3 is R3 plus half of R2. So then this is 0. Of course, these things will change. And now we have made that also 1 and 0 zeros. Now you need to replace. Now you need to replace this with this. Anyway, it is not going to change because anyway it is now also x1. But you need to do that. You need to do that. But anyway, it is not going to do any change. Okay. No, this is after doing the change. Yes, earlier it was S2. You replace it with this because this is my pivot column and this is my pivot row. Now this is my final result. This is my final result. Now you have to interpret. So this is your maximum profit, profit or whatever. Okay. Right, any questions? If S value remain in the stack, how do we get X values? What do you mean by that? Means if this is still less, so then that X value is 0. That is then that X value is 0. That means you don't produce that product. That is what we did for the last example also, right? We got X1, X3, but no X2. So that means don't produce X2. Okay. If slack value is remain, that means this much of slack is there. Okay. If slack value is not there, that means no slack. Okay. So this is our final table. Our maximized value is 33 divided by 2 because this is our Z. That means 16.5. When you get that 33 divided by 2, your x1 will be 3, x2 will be 1.5, right? And your s1 and s2 are 0 because this is two variable thing, right? Two variable thing. Okay. Right. Any question? So there's a high chance that you will get this kind of a two variable question. And examiner specifically asks you to use the simplex method. Okay. Because this approach is given in your notes, in your VLE, you have the UCSC note and supplemental note. In the supplemental note, they have used this. Semester 5, mathematics, VLE. Right. So these are your UCSC notes. Then there's additional resource for linear programming and integer programming. So those are the relevant chapters. There they have explained the simplex method also. You can see this is simplex method. So this simplex table. Okay. Simplex method. So these are the ratios. These are right hand side, and these are the basics you need to set. Okay. You can see this S1 has been replaced by X2, X2. And this explains that this simplex method is also we are approaching the same graphical method. Okay. But we are doing it in a different way. Right. So that's it. That's it. So far they have not asked any simplex method question, but never know, right? Maybe this year. Right. So that is one thing I wanted to explain you. Okay. So the next thing I want to explain you is there's a subset of linear programming questions called integer linear programming. Right. That is also not very difficult, but examiner have not given so far any questions. But you never know, maybe this time the examiner might give. Okay. So therefore, we'll take a small break. Anyway, that won't take much time. There are two approaches. I will explain both the approaches. Okay. Uh, and then we are done. Then I will explain what is knapsack problem also. Then your syllabus is fully done for the statistics and linear programming. Linear programming, 100%. Every concept is explained after today's session. Statistic, every concept is 100% explained. Only thing is linear algebra. I have not explained the latter part because it's very abstract. Okay. But I want to give a sort of introduction into that also. Okay. If we have time today, after doing integer programming, I will give a brief introduction to that also so that you can do your self studies. Okay. What you need is a good solid foundation. Once the foundation is solid, you can understand. All of a sudden, you will find that okay, it's near impossible thing is now possible. So I'm doing this little bit faster because your exams are nearing, right? So you need time for your studies also. Right. So now we'll move on to our next topic, that is integer programming. Okay. Let me open the note. I have shared the note with your WhatsApp group. Okay. Right. So integer programming is a subset of linear programming. So in linear programming, we want to optimize something that value can be a decimal value and so on, right? Maybe profit can be decimal. Okay. And also those constraints can be decimal. Maybe labor hours, either 2.5 hours, 10 hours, or 9.8 hours. Raw materials also, maybe 10 kilogram or 10.5 kilogram. But if it is an integer linear programming question, problem, there's additional constraint, that is your decision variables are integers. Objective functions can be integers or objective function can be non-integer. Like profit, not necessarily integer, right? But if it is number of product, again, it is also integer because you can't release, say, ultimately you are releasing, say, vehicles, you can't release 2.5 vehicles. So therefore, decision variables, either all are integers or some are integers. Objective functions, the result may be integer, may be not integer. Okay. So therefore, now we can subdivide this into three categories also. Pure integer linear programming question, that is all decision variables are integers. Mixed one, that is some variables are integers, some are not integers. It can be decimal. A binary ILP is a very special case. Let's not dig into that. Okay. But I will only explain pure ILP. All decision variables are integers. That is most likely in the exams also, if you get a question, most probably it will be ILP question. And all are integers. So this is a non-linear programming problem and use of graphical method that we have already discussed. So this is our objective function. So, and this is our feasible region. And objective function means it's something like K. We want to maximize the K, right? So that means you get the maximum value when your objective function is something like this. And this is your maximum value. Remember, the maximum value is always one of these corner points. And you can find this value. what are the x and y values, and for that x and y value, what is your z value. That is either graphical method, or today we discuss the simplex method. Suppose for this one, graphical method is good enough. You can find it, right? So then we assume that your x and y are any number. So that is why we got decimal values. So that means that optimum z value, your x is 1.59, your y is 2.73. Now this is non-integer or normal linear programming problem. But if we add a new constraint saying that these x and y values are only integers, then this problem become integer linear programming question. That means now your x can't be 1.59, x can be 1, 2, 3, 4. Y can be 1, 2, 3, 4. There's nothing called 2.73. So then it's a integer linear programming question. If you don't understand, just let me know, okay? Right. So this is the same question. Now we have converted it to integer linear programming problem. Same constraint and same maximization. Okay. Only thing is now we have said x and y are integers. Now when we say x and y are integers, these are the possible points now. Okay. These are the possible points. Say 1 x1 y1 x1 sorry x2 y1 x3 y0 here x2 y2, right? x1 y3 here x0 y4 and so on. Or now only these dots are your possible solutions now, right? There's nothing called somewhere here. But earlier we got this as answer. Now this can't be answer because this is not integer solution, right? Because that is where we got the maximum value, right? So now still my maximization formula is there, line is there. If you keep drawing these maximization lines or keep taking it this way, you will find that this is anyway feasible region. So we are not interested outside this feasible region. That means we are not interested in these dots because these are outside the feasible region. So it can be anything, any dot inside this feasible region. But again, it must be the maximum value. But earlier maximum value was here, but that is not an integer solution. And if you do some trial and errors and play with these parallel lines, you will find that this is your maximum solution, maximum integer solution, because that is the maximum you can get to your z. That means further you can take it, and that value will be x0 y4. Earlier it was not x0 y4. Earlier it was x 1 point something, y 2 point something. But that is not integer solution. Earlier optimum value was 28.65. Now optimum value is less than 20. Now optimum value is actually 28. Okay. And this is the integer solution. Now that is just to explain you the problem and the solutions, right? But I haven't explained you how to get this solution. Of course, this one you may be able to get it by playing with your graph and playing with this line, parallel line. But we need more formal approach so that we can write a program and maybe find it rather than trial and errors. Right. Now, are you clear with the problem? What is the difference between linear programming question and integer linear programming question? Now your x and y values can be something like number of laptops, number of desktops. Now there's no point building 1.2 desktops, 2.5 vehicles. Right. So now how do you do this? How do you solve this kind of problem? So here we do something called LP relaxation. LP relaxation. So that means first we solve this, ignoring this integer requirement. So that means we solve it like normal linear programming. Simplex method or graphical method. So therefore the first part is the same. If you are given integer linear programming question, first forget about the integer part and just solve it, maybe graphically. That is your step number one. Okay. So therefore, if you get an integer linear programming question, first forget about the integer part and solve it, because then you get good amount of marks. Maybe you get 7 out of 10 for the up to that point. So then only you go for the integer solutions. And there are two approaches to get the integer solution. I will take one example from both approach. Right? One is cutting plane method. Other one is branch and bound method. Okay, branch and bound method. Right. Okay. And again, this is just for your information. So remember, there can be a mixed integer problems. If it is a mixed integer problem, only one line is integer. Other part, okay. For example, this can be a possible minimum optimization solution. This can be a possible maximization solution. That means your x value must be integer, but y value can be non-integer. Okay. Or maybe your y value must be integer, x value can be anything. So those are mixed problems. You can see. So your y value must be always of integer, but your x value can be non-integer. It depends, right? Maybe this is raw material. Maybe this is something else, which is integer, discrete. But okay. But we will be only concentrating on full, both are integers situation, right? Not mixed. This is just for your information. What is mean by mixed integer linear problem? Okay. So we will be only concentrating on full integer problem. That means both all the variables are x, y, or x1, x2 must be integers. Because if it is not, it's little bit complex. Still, it's doable, but it will take a little bit more time also. Right. So another very important, very important observation is when you do integer linear programming question, first you do the LP relaxation and just get the normal answer and the optimum value also. Right. So now you want to find the integer solution. Always your integer solution is going to be for your integer solution, the optimal value is going to be either the same value as this or less than this. It can't be bigger than that. So that means if you got a z value earlier, that is this z for this point x5 values, you get a z values. Okay. Say in our case, I think here we got z value as 28.65. But once you, so this is your first step, right? So then you find out what are the integer solutions that gives the best or the optimum z. So that z value is definitely going to less than this if it is a maximization problem. Less than or equal to. It is equal to this if these are already integers. Okay. That is another thing. There can be integer linear programming question, and when you do the relaxation and do it, again you get the integers. So then you are done. By chance it's become already your answer is integers. So then you don't need to do anything. එහෙමත් දෙන්න පුළුවන් question එක. හරි. රිලැක්ස් කරලා කරාමත් ඔයාලට ඉන්ටිජර් උත්තර වෙනවා. එතකොට වැඩේ ඉවරයි. ආයි අමුතුවෙන් refine කරන්න දෙයක් නැහැ. Right. So therefore when you do the LP relaxation, that optimal value is always, or your integer linear solution in optimum value must be always smaller than or equal to that value. Your integer solution's optimal value can't be better than relaxation optimum value. That is common sense. Right? A common sense. මොකද මේක ඇතුළේම දැන් හොයන්න ඕන. මොකද මේ වෙනකොට දැන් වට මේ වෙන එකක් එන්නේ නැහැ හදන්නේ. වෙන එකක් එනකොට ඔතන Z value එක ඊට චුට්ටක් හරි අඩු වෙනවා නැත්නම් සමාන වෙනවා. Okay, so that is a very important observation because that is one of the bases we use in both the approaches. Okay, right. So now let's look at the two approaches of finding integer solution after you already have the relaxation solution. That is just forgetting the integer part and solve it using graphical or simplex method. So the two approaches are cutting plane method and branch and bound method. Okay. So this is sort of a comparison between the two approaches. Okay, two approaches. So cutting plane method is good for small problems with well-behaved solutions, but branch and bound method is good for large problems. Okay, so therefore branch and bound is the standard approach, right? But cutting plane is another approach. You can use it for little bit simple scenarios. Okay, right. So therefore first we'll look at the cutting plane approach, which is actually easier for simple problems. Okay, but for complex problems you need to go for branch and bound. Right. So let's look at what is mean by cutting plane method. If you get a integer linear programming question, it should be a very simple question, right? I doubt whether they will give it or not. Most probably no, but I feel like this time they might give you a simplex method question, not integer, normal question, simplex. Okay. Here maybe they will give you a knapsack problem possibly. Right, knapsack problem. Knapsack problem is not in this note. Maybe I can add it and give it to you, but I will give you a video which explain what is a knapsack problem and how to find the solution using the greedy method. Okay, so that you should be able to understand 100% by looking at the video. I never got a chance to put it into the slides. Okay, so I will share that video later. Anyway, knapsack is the third type of problem under integer linear programming. Okay, so right. Let's first finish the cutting plane method. Now this is the problem. So this is the approach. The cutting plane method focuses on refining the feasible region of a linear programming relaxation. That is you already have got the optimum solution, ignoring the integer part. Okay, you just consider it as any solution is feasible. So that is relaxation. You must already have that solution. Here what we do is we try to refine the feasible region. So right, iteratively adding new constraints. So new constraints are called cuts. So that is why we call it cutting plane. These cuts eliminate fractional solutions. So when we introduce this additional constraint, it eliminates some non-integer solutions. That is the idea, right? So get rid of non-integer solution and reach to an integer solution, right? While preserving the integer solution. So gradually after few iteration, maybe one iteration, two iteration, you will get the optimum integer solution. Okay. Right. So these are the steps. Just solve it as a ILP relaxation, that is forgetting the integer constraint, just solve it. Then iteratively refine it. That means you narrow down the feasible area so that you get rid of non-fractional solutions, Okay. Sorry, get rid of the fractional solutions. You can भाग संख्या तीन solution टिक टिक आइन करना है. Eliminate कर region को पूंजी करना. Right? And you stop it when you get the integer solution, optimal integer solution. It's an iterative approach. The key lazy so it depends on the problem. So some problems is you can get the answers fast. For some problems, getting the answer is not, because this is not a very standard approach. So this is depends so many things you can do. Sometimes it will work, sometimes it will work fast, sometimes it will go slow, sometimes you are not very sure what to do, because this is very open approach. But the second approach is more systematic approach. That is why the second approach is the better formal approach, but this one is a sort of a quick and dirty solution approach. This may work, this may not work. Right. So we'll do only one example. So this is a integer linear programming question. So your first part is forget about this xy is the integer part. Just solve it. Just solve it. This is a super simple question, right? And you will get something like this. So this is my first inequality. 2x plus y must be greater than or equal to 2. So this is 2x plus y is 2. It must be greater than this. And then the next one, minus x2 plus 2y must be greater than or equal to minus 2. So that is, this is that line. This is that line. It must be above this. It must be above this. And so therefore, it must satisfy both. So therefore, this is the feasible region. This is the feasible region. Okay. This region. Okay. So then, this is the optimization formula. That is x plus y is k. That means x plus y can be 1, x plus y can be 2, x plus y can be 3, x plus y can be 4. Okay. So this is x plus y equal k sort of a thing. It can be any parallel line. Any parallel line. And this is a minimization problem. So sorry, I forgot to mention. So this example is not a maximization problem. This is a minimization problem. You need to find the minimum set satisfying this. And remember, the answers must be within this region. Within this region. And this is your parallel lines. So which line is going to, now remember, always the solution is one of the cross point. And you will find that when you simultaneously solve these two straight lines, you will find these values. And when you substitute those values, you will get the minimum Z. Right? Minimum Z. But that is not an integer solution. Why? Because this is 6 divided by 5 minus 2 divided by 5. So we got the minimum, that is the relaxation. Under relaxation, you get the minimum value or the optimum value, that is this. Okay. So that is the starting point. That is our starting point for the, or we have done the step 1. Then you can find the minimum value also by substituting x as 6 divided by 5 and y as minus 2 divided by 5. So basically, this minus this, that is 4 divided by 5. So the minimum value is 4 divided by 5. Okay. But that is not an integer solution, because you get that value when x is 6 divided by 5, y is minus 2 divided by 5. Right. So now we have done the step 1. Under relaxation. Okay. So now what we want to do is add some additional constraints. So that is the idea, right? So remember, solve the LP problem. If the solution is not integer, identify a constraint or cut that exclude the fractional solutions. So that means add more constraints. This is little bit arbitrary. That is why this is not very formal. ඔයාලට පොඩි ලක්කයකුත් තියෙනවනේ මේක හරියන්න. ඔයා කරන වැඩේ හරියන්න. මොකද හරියටම කරන්නේ මොකද්ද කියලා මේ approach එක කියන්න බෑ. ඒ වෙලාවට හොඳ දෙයක් කරලා බලන්න. ඒක හන්දර එක්සැමිනර් මේවයි ක්වෙස්චන් එකක් තාම දීලත් නැත්තේ. මොකද ඒ වෙලාවට කරන දේ ස්ටුඩන්ට් ලාගේ ලක් එකක් බලපානවනේ මේක දැන් එක්සෑම් එකේ කරන්න ගියාම. Right, so this is something that we have in this example. This is something we have done. So that is, we have eliminated one of the variable from our two inequalities. How to do that? Let's say we want to eliminate x, then 1 plus 2 times 2, then 2x and minus 2x get cancelled. Then 5y is greater than or equal to 4 minus 2 is, sorry, 2 plus minus 4 is minus 2. That means y must be greater than or equal to minus 2 by y. That is the additional constraint now we have obtained by combining these two inequalities. We eliminate one variable. So now we have another constraint. It says y must be greater than or equal to minus, this is 2 divided by 5, or minus 4 divided by 10, or minus 0.4. That is additional constraint. Why do we need it? We want to narrow it. එහෙම නැත්නම් කරන්න වෙන්නේ මේ වගේ සරල රේඛා ඇඳලා කොහෙද කැපෙන්නේ කියලා බලන්න. හොඳම අඩුම වෙන්නේ කොතනද කියලා. Okay. Right. So now we have additional constraint, that is y must be greater than minus 2 by 5. But remember, now we are in the integer solution. But y can't be a fraction. Now this says y must be greater than or equal to minus 2 by 5. But y can't be a fraction. This is a negative fraction. This is a number between 0 and minus 0 and, sorry, 0 and minus 1. If that number must be between, must be bigger than number between 0 and minus 1, right? So that means it must be bigger than 0, because this kind of value can't be a solution. It says bigger than this value, but it must be integer. So therefore that means it must be bigger than 0. It must be bigger than 0, because your y can't be a negative fraction. So the next bigger value is 0. So therefore we can say safely y must be bigger than this. As an integer solution, y must be bigger than 0. So therefore now we have our additional constraint, that is y must be bigger than 0. So this one we can write it like this, because y is an integer. Y is an integer. ඒකෙන් කියනවා වෙනවා අපිට මොකද්ද? y can't be negative 1. y එක ඍණ එක වෙන්න බෑ. මොකද y එක මීට වඩා ලොකු වෙන්න ඕන. එහෙනම් විශාලයි බෙස්ස ගමන ලැබෙන්නේ. So that means our feasibility region is now above this line, because y must be bigger than or equal to 0. So that means we eliminate this part. ඔන්න ඔය කැලේ අයින් කළා දැන්. ඒක එතන තමයි optimal solution එකක් තියුනේ නේද? අපි දන්නවා දැන් මේක ඇතුළේ මේ කැලේ වෙන්න බෑ, because of this additional constraint. That constraint is a logical constraint, because we got it from these two by doing valid arithmetic operations. Okay, so that means now we have narrowed it to this area. This area. Okay, මේ දිගටම යනවා හරි. ඉස්සෙල්ලා තිබිච්ච මෙන්න මේ කැලේ දැන් නැහැ. So now our feasible area is somewhere here. Right, somewhere here. Okay. So that is our first cut. ඔතනින් උත්තරය આવත් හොඳයි, නැත්නම් තව පාරක් කට් එකක් දාලා තව අඩු කරලා බලන්න. ලොකු කට් දාන්නත් බෑ, එතකොට ඔයාගේ feasible solution එක නැති වෙනවා. චූටි කට් වෙන්නත් ඕන දාන්න. Right, so now this is our feasible area, green area, because y must be bigger than 0. This is not y is bigger than 0. Y is our second variable. Okay. Right. Now, if you look at this, right, you will find that earlier your solution was this. Look at now. You need to listen to me very carefully now. Earlier, this was our solution, optimized solution, or the minimum solution in this case. Okay. But now, earlier we had this region also. Now your region is here. Now your region is green area. Right? Since y must be integer greater than 0, greater than or equal to 0, our new feasibility region is further narrowed to above the x-axis. Yes, that is green area. Now we can clearly see that z equal x plus y line has minimum value in the new narrowed feasible at 1, 0. This is where you have the new mid value because that cut this parallel line. Of course, you can write any parallel line, but it is going to cut here. And it must be the minimum. Okay. So therefore, this is the best solution, but it is not integer. But this is integer best solution after this cut. Because this is integer solution. X is 1, y is 0. X is 1, y is 0. මේක ටිකක් කර ආවිතරි හරි ඒකයි මම මේක එච්චර හොඳ සිස්ටම් එකක් නෙමෙයි කියලා. හැබැයි ඔයා පොඩි ලොජික් පාවිච්චි කර කර මේ නැරෝ කර උත්තරයක ලං වෙනවා. ඉන්ටිජර් උත්තරයක ලං වෙනවා. Okay. And therefore our minimum value is when x is 1, y equals 0, right? X is 1, y equals 0. That is basically 1. Minimum value किया देने 1. अपनी इससे लायक minimum value किया क्या? मैंने मेरे को substitute करा वहाँ पे value को, substitute करा वहाँ पे value का. Then අපිට එනවා කීයද minimum value 1 කියලා. That is the answer. Okay. Right. So the second approach is little bit more formal. So this approach is right little bit fussy, right? Fussy, and you don't know exactly what to do with your things and blah blah blah. Okay. So let's move on to the second approach. Second approach is little bit more formal, little bit more detailed, but it's more formal. You will feel more comfortable with the second approach, though it is little bit lengthy. The second approach is called branch and bound method. Forget about the exam. Exam එක අමතක කරත් ඔයාලට optimization තමයි මේ ජීවිත ලෝකේ තියෙන වැදගත්ම topic එක. අපි හැමෝම try කරන්න මොනවාද? Profit එක optimize කරන්න, cost එක minimize කරන්න. හරි හැමෝම කරන්නේ ඔක තමයි. විද්‍යාඥයෝ බලන මිනිසුන්ගේ ආයු කාලය maximize කරන්න. right? Engineers ලා බලනවා ඒ component එක fail වෙන්න තියෙන time එක අඩු වැඩි කරන්න. ආර්ථික විද්‍යාඥයෝ බලනවා රටේ උද්දමනය අඩුම කරන්නේ කොහොමද කියලා මොන variables ඒගොල්ලෝ දැන් variable වෙනස් කර බලනවා නේද? හොඳට මතක ගන්න මහා බැංකුවේ ඉන්නේ කවුද? මහා බැංකුවේ ඉන්න ආර්ථික විශේෂඥයෝ ඉන්නවා. economists ලා. So they have done PhDs, first degrees in economy. ඊළඟට මහා බැංකුවේ ඉන්නවා maths කරපු අය, statistics කරපු අය. ඔය දෙකවල තමයි මහා බැංකුවේ ඉන්නේ. මහා බැංකුවේ අයගේ ඒගොල්ලෝ දන්න සැලරි ඉතා වැඩි නේද? ක්ලාක් කෙනෙක්ට ලක්ෂයකට වැඩි ගන්නවා. මම හිතුවා ලක්ෂ 3ක් විතර ගෙවන ක්ලාක් කෙනෙක්ට ඔය තේ හදන කෙනෙක්. බොරුණ ඇඩ්වර්ටයිස්මන්ට් එක අරන් බලන්න ගැසට් එකක දාලා තියෙනවා. ඒ අනිත් එක පඩි දා ගන්න පුළුවන්. අනිත් එක පඩි. ඒකනේ ඒගොල්ලෝ අර EPF එකේ හෙයා කට් එකක් කරා නේද? හැමෝගෙම EPF ETF. ඒගොල්ලෝ කියන්නේ අපේ හෙයා කට් කරන්න බෑ. පස්සේ ඒක පාර්ලිමේන්තුවලට තියනවා කියලා එහෙනම් වලියක් දාලා තමයි රිවර්ස් කරේ. ඒතර එතන ඉන්න කවුද? ඉකොනොමිස්ලා ඉන්නවා. ඊළඟට එතන ඉන්න මැතමැටිෂියන්ස්ලා. ස්ටැටිස්ටිෂියන්ස්ලා. දැන් ඉන්න තුන්වෙනි වර්ගයක්. third category. මහා බැංකුවේ ජොබ් එකකට යනවා. හැබැයි ෆස්ට් ක්ලාස් එකක් තියෙනවා. මහා බැංකුවේ ජොබ් එකකට යන ෆස්ට් ක්ලාස් එකක් තියෙනවා. ඒ කියන්නේ සෙකන්ඩ් අප් එකකටවත් ගන්න නැහැ මම හිතන්නේ. second අපේ එකට සමහරට ගන්න ඇති සාමාන්‍ය first class එකක් තියෙනවා. තුන්වෙනි වර්ගය තමයි කවුද? data scientist. ඒ කියන්නේ IT කරලා computer science කරලා IT කරලා data science පැත්තෙන් specialize කරපු කට්ටිය වල. මොකද data science වලින් තමයි මේ computer පාවිච්චි කරලා මේ integer programming linear programming තමයි තනි කර කරන්නේ. ඕවා අතින් කර කර ඉන්න බෑ. ඕවා කරන්න ඕන දැන් tools වලින්. හැබැයි කරන එක්කෙනා theory එක දැනගෙන ඉන්නවා. tool එකෙන් කරාට මොකද්ද මේ කරන්න කියලා. ඔන්න ඔය තුන් ගොල්ලෝ එකතු වෙලා කවුද? economists ලා, mathematicians ලා, statisticians ලා, data scientists ලා තුන් ගොල්ලෝ එකතු වෙලා තමයි මේ මහ බැංකුව තනි කර run කරන්නේ. ස්වාධීනත් කරන්න පහුගිය දවස්වල නේද කාටවත් අත ගහන්න ඉන්න බෑ කියලා අපිට ඕන විදිහට අපි වැඩ කරන්න ඕනේ කියලා. මොකද ඒගොල්ලෝ තනි කර විද්‍යාවෙන් වැඩේ කරගෙන යන්නේ. ඒකන් තමයි උද්දමනේ බහගෙන යන්නේ. උද්දමනේ බහගෙන යන්නේ. ඒගොල්ලන්ට ස්වාධීනත්වයේ විදිහට පනතකින්ම දුන්නා. පාර්ලිමේන්තුව අපි දැන් උඹලට කරදර කරන්න යන්නේ උඹලා වැඩේ කරගෙන බලන්න උඹලා ප්‍රොෆෙෂනල්ස්ලා. එනි උඹලා ප්‍රොෆෙෂනල්ස්ලා විදිහට කරපාලා මේ ආර්ථිකය ගොඩ දාගන්න. So that is one of the act passed during the last that means after Gotabaya period. Okay. So these are the things they use. මේවා තමයි තියෙන tools. Okay. මොකෝ ඒගොල්ලෝ කොට නැගිලි හදනවා ඒගොල්ලෝ නේද? ඒගොල්ලෝ බිල්ඩින් හදන්නෙත් නැහැ, වාහන හදන්නෙත් නැහැ, විදුලිය දෙන්නෙත් නැහැ. ඉන්වෙන්ටරි මැනේජ්මන්ට් සිස්ටම් හදන්නෙත් නැහැ, ඕඩර් ප්‍රොසෙසින් සිස්ටම් හදන්නෙත් නැහැ. ඒගොල්ලෝ කරන්නේ ඔන්න ඕක තමයි. ඊළඟට ඉන්වෙස්ටර්ස්ලා optimize the profit. මේ shares ගන්න අනිත් shares ගන්න. shares ගන්නකොට මේකෙන් කීයක් ගන්නවද අරකින් කොච්චරක් ගන්නවද? optimize කරන්න. return on investment. එතකොට කියනවා හරි මේ shares වලින් 50000ක් ගන්න. මේ shares වලින් 10000ක් ගන්න. අර shares වලින් 15000ක් ගන්න. එතකොට සාමාන්‍ය මිනිස්සු බෑ මුට පිස්සුද මේ. වැඩිම එකෙන් ඔක්කොම ටික ගන්න ඉක්කොනේ. එහෙම බෑ. මේකේ risk තියෙනවා. So optimization problems. Okay. Right. So let's move on to the branch and bound method. Right. So this is we'll straight away use the example. So this is our problem. Maximize z, which is 5x1 plus 4x2, subject to these constraints, two constraints, because we want to make it simple. Right. And x1 and x2 are non-negative integers. Okay. But to make our life easy, this particular example has assumed that even z is integer. Z is integer. හරි z උත් integer කියලා අරගෙන තමයි මේ question එක හදලා තියෙන්නේ. මොකද ඒකවල ඉක්මනට eliminate කරලා උත්තරයක් ගන්න පුළුවන්. Right. First, what is the first step? Forget about integers, just solve it. Just solve it. Okay. Graphical method. So then one of these must be your optimum values. And you will find that by substituting in this optimization formula, this x and y value 0, 5, 0, 0, 4 point something you will get. Okay. And this value, so you will find that the maximum value is at this point. So that means this is the maximum optimum value. This is a maximization problem. So that is our step number 1 is done. Now we know the maximum or the optimum value is at 3.75, 1.25. And that value will be 23.75. Right? That is when you substitute it in this formula. So that is step number 1 is the same. With the cut approach or branch and bound approach. Right. That is the relaxation problem. We have relaxed the integer part. Now you know that yes, this is the optimum solution, but this is not integer solution. So these are the possible points. Right? So these are the possible integer solutions, assuming that both x and y are integers. But now our task is find out whether is it this, is it this, is it this, is it this, or is it somewhere here, somewhere here, somewhere here. කොයි එකද කියලා බලන්න. මොකද මේ region එක ඇතුලේ වෙන්න ඕන. region එක ඇතුලේ වෙන්න ඕන. Okay. Right. So now we are going to do the branching. Now remember, this is our optimum point after relaxation. But this value is not integer. So that means it must it can't be anything between 3 and 4 because between 3 and 4 all the values are non-integers. This is more logical approach. මේක ඇවිල්ලා logic එකක් විතර ඕන කෙනෙක් තේරුම් ගන්න පුළුවන් මේ කරන වැඩේ. අර කලින් වගේ නිකන් අරක වැඩි කරලා බලනවා එහෙම කරන්නේ නැහැ. So if this is my optimum solution's x value, which is not an integer, so then definitely it can't be the possible solution under integer leap optimization. So then it must be either 3 of between 3 and 4. කියන්නේ එක්ක මෙතන 3ට වඩා වැඩි වෙන්න ඕන, එක්ක 4ට වඩා වැඩි වෙන්න ඕන. මේ දෙක අතර වෙන්න බෑ. ආයිත් කරන්නේ මේ region එකක් අයින් කරලා දානවා. So therefore our solution must be, integer solution must be either greater than or equal to 4. Okay, x1 must be greater than or equal to 4 or less than or equal to -3. Those are the two branches. ඒ කියන්නේ අපි මේ කෑල්ල අයින් කළා දැන්. මේ කෑල්ල අයින් කරා. දැන් අපිට ඇත්තටම region දෙකක් ආවා. මොකද මේ කෑල්ල තියෙන්නේ non integer solution නම්. So now we have branched it to this part or this part. අපි දන්නේ කොයි පැත්තේද උත්තරේ තියෙන්නේ කියලා. But definitely not here because these are not integer solutions. Okay. So now we have done the first branching. Okay. So each branch means addition of a constraint to the original LPP. Branching always worsen the value of Z. The optimum Z එක ඇවිල්ලා ඉවරයි relaxation. So the optimum is 23.75. We are not going to get anything better than 23.75. That is obvious. අපිට වෙන්න ඕන මේ 23.75ට වඩා අඩු එකක්. හැබැයි ඒ අඩු එකයි හොඳම එක හොයන්නයි මේ හදන්නේ. හරි. අඩු එකක් කියලා මේ තියෙන එකක් අරන් ඉල්ල හරියන්නේ නැහැ. But definitely our integer solution is going to be lesser than or equal to 23.75. In this case, lesser than because these are not integers. Right. So now you have the two branches, less than or equal to 3 or bigger than, greater than or equal to 4. Equal mark here තියෙන බය නෙපා. Okay. So now you can see we have eliminated this part. This one ඔය කැලේ අයින් කළා දැන් දී. මොකද ඒ කැලේ solutions integer නෙමෙයි. Integer නෙමෙයි. So this is this branch and this is this branch. Okay. So AGED is now one feasible region and HFB or HBF is the other region. Make it perfectly logical. අර වගේ අපිට දේවල් කරන්න. වැඩි අමාරුයි දිග වුණාට මේක perfectly logical දේවල් කරන්න. කල්නුත් කරේ logical දේවල් තමයි. නමුත් ඒක පික් කරගන්න හරියට කතන්දරයක් නැහැ එතන. ඒ වෙලේ හොඳ එකක් හොයාගන්න ඕනේ. මෙතන එහෙම කරන්නේ. Right. So now we have the two branches. Okay. Now you need to do a clever thing. Okay. Now remember, this is my, you can draw these vertical lines. And you want to find this particular point. Okay, let's first look at the left side. That is less than or equal to 3. Less than or equal to 3. So remember, this line is x1 plus x2 is 5 line. So that means we are going from through this line. Right? Where x1 is 3. Now you can find what is this value by substituting the x1 equal 3 in this equation. Because you are going through this line. Right? So therefore, substitute x1 equal 3 to this equation and you will find the x2 is 2. That means now we have found a solution, integer solution, that is this point, which is x1 equal 3 and x2 is 2. How do you find x2? By substituting this because it is in this line. This point is in this line. And it is an integer solution, which is good because these are integers and this is 23. Of course, it is less than 23.75. Obviously, it is going to be lesser. You are not going to get better than this. Then what about the right hand side? Right hand side. So right hand side means we need this point, which is when x1 is 4. x1 is 4. Then you need to find what is y value. But how do you find the y value? Now this point is in this line. So then use this equation. Substitute x1 in this equation and find x2. And you will get x2, but it will be a decimal value. It will be a decimal value. So that is an unfortunate decimal value. And therefore Z is also decimal value. So that means now this is a final node. You don't need to further refine it because we got integer solution. But you don't. But we don't know whether this is the optimal solution. But this is final solution for this branch. You don't need to further branch because we got integer. But still, you don't know whether this is optimal because maybe from here we get the optimal, right? But this is not an integer solution. Therefore, we need to further branch this. Okay, further branch this or logically decide whether are we going to get a better solution from this branch. එක්ක මේක branch කරන්න ඕන. හරි. එහෙම නැත්නම් ඔයාලට logic එකකින් බලන්න ඕන මේක මේ පැත්තෙන් branch මේ මීට වැඩි හොඳ solution එකක් ගන්න බැරිද කියලා. Okay. Right. So anyway, this is not a final solution, but it's a non-integer solution. So because it's a non-integer solution, this is not a final solution. Final solution එකට කියන තව නමක් තමයි fathom node එක. Fathom node එක කියන්නේ final node එක. එතනින් එහාට කරන්න දෙන්නේ මොකද integers නේ. But this is not a fathom node. Now read this. Since we need to move along that line, right? අපි ඒක තහඳ තමයි අපි මේ equation එකට දාලා ගත්තේ. මේ equation එක දාලා ගත්තොත් මොකද මේ line එකේ තමයි මේ point එක තියෙන්නේ. හරි? Since we got a non-integer solution, we need to think of further branching. Then අපිට තව branching කරන්න වද කියලා හිතන්න වෙනවා. Because this is not an integer. That means you need to further branch it. But look at, however, new Z value is 23.33. අපිට ආපු අලුත් Z value එක කීයද? 23.33. So this is a non-integer solution. Right? But this Z value is worse than this. මීට වඩා සවුත් වෙයි. Sorry, it's better than this. Sorry, not worse than this. Sorry. This is better than this. This is 23.75. This is 23. This is 23.33. Okay. Then make ඊළඟ branch එකට යන්න ඕන හරිනම්. Because this looks better. ඒ කියන්නේ මේ branch එක වැඩි හොඳයි. මොකද මෙයා අරයට ළඟින් ඉන්නේ. හරි. ඊළඟ branch එකට යවා ගන්න නැතුව මේක නවත්ත ගන්න ඕන නැද්ද? මේ question එක හදපු එක්කන අලුතෙන් මේකක් දාලා තියෙනවා මොකද්ද? එයා කියලා තියෙනවා නෑ නෑ මේ ඉසෙදුත් integer වෙන්න ඕන කියලා. හරි. ඉසෙදුත් integer වෙන්න ඕන කියලා. ඉසෙදුත් integer වෙන්න ඕන කියලා දාදී නැත්නම් මේක දැන් ආයි branch එකට ගිහලා ආයි සුළු කරන්න වෙනවා. So එතකොට එයා කියනවා නෑ ඉසෙදුත් integer වෙන්න ඕන. එතකොට 23.3 තියාවට පස්සේ ඕක integer නම් ඉසෙත් කියන්නේ ඕකත් මොකද්ද? 23ම තමයි. right 23 ම තමයි. හැබැයි 23 එන්නේ non integer values වල. එහෙනම් මේක තව optimize කරනකොට 23 වලට තවත් අඩු වෙනවා. So therefore, no need to further branch, assuming that my Z is also integer. So therefore, it can't be better than 23. Okay, 23 වෙන්න පුළුවන් මේ පැත්තට. හැබැයි 23 ට වඩා better වෙන්න විදියක් නැහැ. Because this is not 22 something. කොහොමද 22 something වෙන්න විදියක් නැහැ. මෙතන තියෙන්නේ 23.75. හරි. ඔය ඊළඟ branch එකට යන්නද නවත්ත ගන්න තමයි කියලා තියෙන්නේ integer කියලා assume කරමු කියලා. එතකොට අපිට කැල්කුලා මේකේ ඉන්න පුළුවන් නම් මොකද්ද? හොඳම 23 ම තමයි. ඒ එහෙනම් ඉතින් මේ දැන්ට අපිට 23 ඇවිල්ලා තියෙනවා නම් so this we can take this as a optimum integer solution. Okay? And that's it. Whether you get this kind of question for the exam or not, so you must have a bit of a feeling about these optimization problems. Okay? Right? Non-integer solution, but further branching cannot improve it. So therefore, we take it as a final node. Okay. So therefore, optimal solution is this. That is x equal 3, x1 is equal 3, x2 equal 2, and z is 23. So the optimum integer solution is 23. So this is another example, second example. Okay. So this is minimization problem. Minimization problem that you should be able to understand by yourself. Branch දෙක කඩනවා. මම වීඩියෝ එක දාලා තියෙනවාට. හරි වීඩියෝ එකේ link එක දාලා තියෙන තුන අන්තිමට. අර වීඩියෝ එක බලුවම තේරෙයි. හරි. ඒක branch දෙකකට විතර ගිහිල්ලා තමයි ගන්න. branch දෙකකට විතර ගියොත් අන්තිම උත්තරේ එන්නේ. And this will be your final solution. Okay? Final solution. It's a very interesting thing, but I don't think that you will get this kind of question for exam. Okay, right? Most probably you will get a non-integer question. Okay. හැබැයි මේ පාරාවෙන් අහන්න තියෙනවා knapsack problem එකක්. පොඩි knapsack එකක් දීලා optimum value එක මොකක්ද කියලා. හරි. I will give you a recording for video for that. මේක explain කරන මොකද්ද knapsack එකක් කියන්නේ? කොහොමද knapsack එකක් optimize කරන්නේ? ඒක ඉතාම සරල වැඩක්. හරි. එකපාරක් බලපුවම තේරෙයි. I will put it there.
Hi. Our next problem is job sequencing with deadlines. This problem, we are going to solve it using 3D method. So first of all, we will understand what the problem is. Already.
So make sure you go through that, okay? Make sure you go through that and understand it. Okay? Right. So today I want to finish your syllabus, okay? So therefore we'll take 10 minutes break and I will give you a brief introduction into, now remember we have done part of linear algebra, okay, part of linear algebra including vectors, okay, but I want to give a little bit of a more insight into the second part. ඔක්කොම කරන්නේ නැහැ මම පොඩි idea එකක් දෙන්න මොකද්ද vector space එක කියන්නේ කියලා. හරි. That is after the note after the break. And I have prepared a partial note also. That note also maybe I can share you. හැබැයි ඒක full note එක නෙමෙයි මුළු syllabus එකම කව වෙන්නේ නැහැ. syllabus එකෙන් පොඩි භාගයක් විතර තමයි කව වෙන්නේ. හරි. අර නැත්නම් equation එකේ පුළුවන් ටිකක් ඔයාලට උඩ කරගන්න පුළුවන්. Right. Vector spaces and linear transformations. Right. So this note is not finished actually. I don't think that I will have more time to finish this. Maybe for the next batch I can finish it. Right. I gave you a very good introduction into vectors. Now remember vector and vector space are two different things. Right. One thing is vector space. Now in all syllabus what you had was vectors. I shared you the vectors note. That is, you look at vectors as not like a math subject, like a physics. Vector has direction, vector has a magnitude, vector can be force, vector can be velocity, vector can be acceleration. But in your new syllabus, what you have is not vectors, what you have is vector space. Vector space. So vector space is not vector. Vector is not abstract concept. Vector is something you can touch, feel, right? Sense in the form of force, pressure, velocity, acceleration. But vector space is a mathematical concept. Like you can't touch fire, right? But you can think about it. You can think about this. So vector space is something like that. So you can, so 5 is a abstract concept, but you can think of 5 toffees, 5 trees, but 5 is abstract. So vector space is also like this 5. Vector is something like this 5 toffees, 5 children. Okay. Right. So we'll move on to the vector space. Right. First of all, you must know what are the types of numbers. This is from your semester one introductory maths. So we have the natural numbers represented by capital N. That is 1, 2, 3, 4, 5, and so on. Whole numbers positive. Then whole numbers, we include 0 also. So natural number 0 is not there. Whole number 0 and any positive integer. Then we have integers. Okay. So integers are positive whole numbers, negative whole numbers, and 0. Then we call it integers. He said, remember today we discussed about integer linear programming? Integers, he said. Okay. So then we have rational numbers and irrational numbers. So rational numbers are numbers we can write it as division of two integers, p divided by q. So any integer is a rational number because say integer 3 I can write it as 3 divided by 1. So if you can write that number as a division of integers, it's a rational number. So all natural numbers, whole numbers, integers are rational numbers. But other than that, something like half, rational number. 3 divided by 2, minus 3 divided by 5, and of course 0.5 because 0.5 is half is division of two integers. 0.7 because 0.7 is 7 divided by 10, division of integers. This is same as this. So those are called rational numbers. Q. So then mathematicians, for very long period, mathematicians thought only rational numbers are the biggest, even the Pythagoras time. But one of the Pythagoras follower became Golekya. So he came up with idea that there are irrational or there are numbers which are not rational. That means you can write it as a division of integers. So root 2, root 3, root 5, pi, e, those are irrational numbers. Okay. ඇත්තට Pythagoras ප්‍රමේයම තමයි ඔකට ෆවුන්ඩේෂන් එකක් දාලා දුන්නේ. For example when Pythagoras තමයි ඔක කතන්දරේ. හැබැයි Pythagoras ඔළුවේ තියුන්නේ නැහැ මෙහෙම නම්බර තියනවා කියලා. Pythagoras theorem says when you have a rectangular triangle, summation of the square of the two sides is same as summation of the hypotenuse. Sorry, square of the hypotenuse. And if this is 1, this is 1, this is what? 1 squared plus 1 squared is 2. This is root 2. So root 2 is a length. Well, how do you say root 2 is a length? Because when this is 1, and this is a rectangular triangle, this length is root 2. But mathematicians found that there's no way you can write this number as a division of two integers. But there's number like this. There's a value. So therefore they call them irrational numbers. But if it is 3 and 4, then 9 plus 16, 25, then it is 5. 5 is a rational number. But root 2 is irrational number. Right? So, and if you take both rational and irrational numbers together, we call it real number. Right? Real number. And when you draw number line, basically we draw the real number line. When you draw the Cartesian plane, basically what you have is one real number line, another real number line. So that means in a Cartesian plane, you can have root 2, you can have 5, you can have 0.3, you can have 1. Any integer, rational number, irrational number can be represented in real number line. For Cartesian plane, which is two real number lines in vertical or perpendicular. Okay. So then we have imaginary numbers. Right? That is square root of a negative value. Because when you multiply two negative numbers, positive. Two positive numbers, again positive. But now we have a number which is square root of a negative value. Say negative root 3. So this can't be positive, right? Positive into positive is square root එක නේ එක නම්බරයක් හොයාගන්න ඒක යාගෙන් වැඩි කරලා මේක එනවා. පොසිටිව් වෙන්නත් බෑ එතකොට ධන වෙනවා. මේ නම්බරේ නෙගටිව් උත්තරයක් වෙන්නත් බෑ නෙගටිව් into නෙගටිව් පොසිටිව් වෙනවා. ඒතකොට ගොඩක් for a very long period mathematicians thought there can't be such case. There can't be such numbers. There are no such numbers. But later they found that yes, there are numbers. Such numbers, and now we call them imaginary numbers or lateral numbers because those numbers are in a lateral plane to the normal real plane. මේ නම්බර තියෙන real plane එකට perpendicular ලම්බක තලයක තමයි මේ නම්බර තියෙන්නේ. මේ නම්බර තියෙන මේක විතර xy වල z plane එක නෙමෙයි. ඒ විතර real මේකත් real line එකක් මේකත් real line එකක් මේකත් real line එකක් නෑ මේක වෙන කතාවක්. These are two real number lines. There's another plane, but that is not a real plane. It's an imaginary plane. Okay, වැඩි කරද්දී තමයි explain කරන්න පුළුවන්. හරි. So I'm not going to do that. But just remember there's something called imaginary numbers, which is a big topic in A-level maths. Okay. If you are interested in imaginary numbers, you need to separately learn it. Separately learn it if you are really interested in that. And then complex numbers, that is imaginary number part plus real number part together. Okay. Then we call it complex numbers. සංකීර්ණ සංඛ්‍යා. හරි. දෙවට ටික ඔළුවේ තියෙන්න ඕන වැඩේට වහින කලින්. මොකද abstract කතන්දර ඉගෙන ගන්න නම් මේ පොඩි abstract දේවල් ඉස්සර තේරුම් ගන්න ඕන. Imaginary number එකක් කියන්නේ මොකද්ද? complex number එකක් කියන්නේ මොකද්ද? rational number එකක් කියන්නේ මොකද්ද? irrational number එකක් කියන්නේ මොකද්ද? That is revision. Okay. Right. So now we'll move on to your syllabus. මම කියවගේ syllabus එකේ ඔය topic එකෙන් 10%ක්වත් මම කරන්නේ නැහැ හොඳේ. Fields. So mathematicians have built another concept called now fields. Remember in maths there are concepts, right? Numbers, real numbers, rational numbers, irrational numbers, imaginary numbers, complex numbers. Sets is another concept. Sets, kulaka. Sequence and series, another concept. Geometrical shapes, triangles, parallelograms. Now we have another concept. Matrices concepts. Now we have another concept called a field. It's a part of the abstract algebra. What is meant by field? This is how mathematicians define field. Field. Okay. In mathematics, the field is denoted by capital F, equipped with two operations, right? Called addition and multiplication. Okay. If a particular set of things satisfy or support add operation and multiply operation, we call it a field. So when we say addition, implicit subtraction is there. When we say multiplication, implicit division is also there. Okay. And if you look at our integers, is it a field? Rational numbers, is it a field? Real numbers, is it a field? So that you need to think now. You need to think now. ඔය කියනවා fields ද කුලක වගේ එකක් field එකක් වෙයිද? That means is it going to satisfy this definition of a field? So field is concept, any concept that satisfy addition and multiplication. Those two properties. තව ටික අපි define කරනවා what is meant by vector කියලා. තව කතා කරලා. Fields, vectors. Right. So these are the properties of fields. Okay, so these are direct from your note, UCSC note take me guarantee, na? So this is the fundamental properties. You call it closures. If A and B are fields, A plus B must also be a field. A multiplied by B must also be a field. එහෙම වෙන්නේ නැත්නම් ඒක field එකක් නෙමෙයි. හරි. ඒවා එකතු කරාමත් ඒ જાතියම එන්න ඕන. වැඩි කරාමත් ඒ જાතියම එන්න. Then the associativity principle property. A plus B plus C is equal to A plus B plus C. A into B into C is same as A into B into C. Commutativity, A plus B is same as B plus A into B is same as B into A. So that means fields satisfy these properties. Field එකක් නම් ඒක එයා මේ properties satisfy කරන ඕන field එකක්. Then distributivity, A dot B plus C is A dot B plus A dot C. That dot means multiply. මේ vectors නෙමෙයි යා. Then there's a concept called identity for fields. There's a additive identity, multiplicative identity. Additive identity is 0. Right? Because when you add 0 to a field, you get the same field value. So then this is the identity for addition. What is the additive identity? 0. If you multiply a field value by a number, if you get the same value, that is called multiplicative identity. Yes, there's such identity called 1. The additive identity is 0, multiplicative identity is 1. Then we have a concept called additive inverse and multiplicative inverse for fields. Additive inverse is when we have a field value, when you add that value, you must get the additive identity. Additive identity is what? 0. So when you have a field value, when you add its additive inverse, you must get 0. If you can find such a number, that is the additive inverse. Of course, that number is what? Minus f. If your field is 5, it's minus, its additive inverse is minus 5 because 5 minus 5 is 0. That is how you define additive inverse. First, we have defined what is additive identity and multiplicative identity. Then what is your multiplicative inverse for a field? If you have a field, when you multiply it by that value, if you get the multiplicative identity, which is 1, that is your multiplicative inverse. Okay. Okay. So that is usually 1 over that value. Not usually, that is 1 over f value because f into 1 over f is what? Okay. So that is called a field. That is called a field. That means it must satisfy addition and multiplication. When you add two fields, you must get a field. When you multiply fields, you must get a field. And it must support these properties. And it has additive identity in multiplicative identity, additive inverse and multiplicative inverse. So what satisfies what up again fields here. Okay. So what are the fields? Then what are the real world example for fields? මොනවාද ඔය satisfy දේවල් තියෙනවා සාමාන්‍ය ජීවිතේ. Oh, real numbers. So real numbers means real numbers satisfy කරනවාගෙන ඕන number එකක් satisfy කරනවා. මොකද if you take the real number set, inside the real number set you have the rational numbers because any real number is either rational number or irrational number. And inside rational numbers you have the integers. Inside integers you have the natural numbers. So that means any number, right? Any real number is a field, but not on the real numbers. Complex numbers, the real numbers field එකක් නේ අනිවාර්ය rational numbers field එකක් එන්න එපා. Okay. Rational number field එකක් එන්න. And not only that, even complex numbers are fields. That means when you add two complex numbers, what you get is a complex number. When you multiply two complex numbers, what you get is a complex number. So therefore, yes, complex numbers are also field. Okay. Then there's another concept called finite field, right? So that means it's an integer modulo. Mod arithmetic kara. But integer modulo of a prime number. Prime numbers modulo also fields because that also going to satisfy addition property and multiplication property. Okay. So you think about it. What you උදාහරණයක් කරන් බලන්න එහෙම වෙනවද කියලා. එතකොට chat GPT එකෙන් අහන්නේ ඇයි මේ finite fields කියන ඒවා fields විදිහට ගන්න කියලා. Right. So these are non-examples. Non-examples. දැන් මෙතන පොඩි හුටපටයක් තියෙනවා. මෙතන අපි කව real numbers fields කියලා. Real numbers වල තියෙන integers fields වෙන්නේ නැත. Right. Why not? Closure under addition, subtraction and multiplication. This property holds for integers. ඒක හරි. When you add two integers, it's an integer. When you multiply two integers, it's an integer. When you subtract, it's an integer. Okay. And additive and multiplicative identities are also there. Okay. That is 0 and 1. A property is හරි. තාම field එකට ඕන properties satisfy. Then additive inverse is also there. If you have plus 5, additive inverse is minus 5. If you have minus 3, additive inverse is plus 3. ඒකත් අවුලන්නේ. තාම satisfy කරනවා යා. Then what about the multiplicative inverse? So that means when you multiply a number by another number, you must get 1. One no property is satisfied. Because if you're, that means if I have number, when you multiply by that number by its inverse, multiplicative inverse, you must get 1. If it is now if it is 5, it must be multiplied by 1 over 5 to get it 1. But that now if this is an integer, but this is not integer. අපිට මේ જાතිය වැඩි කරාම තව ඉන්ටිජර් එකකින් වැඩි කරාම එක එන්න ඕනේ නේද? හැබැයි ඉන්ටිජර් එකකින් වැඩි කරාට කවදාවත් එක කියලා එන්නේ නැහැ. Okay. This is not an integer. So therefore integers does not support multiplicative inverse. Because integers multiplicative inverse is not an integer. Multiplicative inverse is an integer. So therefore integer is not considered as field. On integers field නෙමෙයි. Okay. Integers field නෙමෙයි. දැන් උතන පොඩි හුටපටයකුත් තියෙනවා. Real numbers field නම් කොහොමද integers field නොවනේ? මෙතන real numbers කියලා හරිනේ in general real numbers. හරි? එතන integers ඇත්තටම අතහැරලා අරන් තියෙන්නේ. කියන්නේ integer නොවන numbers තියෙනවනේ. ඒව fields. Okay, non-integer real numbers. So therefore, definitely integers are not fields. Okay. And finite fields with fields samay. Prime number එක mod value. Right. Okay. So these are popular non-fields, integers, matrices. So the main reason why matrix is not field is when you add two matrices, it's a matrix. That is fine. මතක නේද? Field එකට field එක එකතු කරාම field එකක් එනවා. When you multiply two matrices, it's a matrix. That is also fine. But matrix multiplication is not cumulative. Right? One of the property of field is right. A plus B must be B plus A. ඒක හරි. Right? If you have two matrices, right? Whether you add this and this, say my matrix is 2, 3, 1, 0 plus minus 1, 2, 3, 1. This is same as minus 1, 3, 2, 1 plus 2, 3, 1, 0. Yes, make hurry. Matrix එක මාරු කරාට ඒක උත්තරය. වැඩි කරද්දී ඔක හරියන්නේ. So this is not going to satisfy for matrices because in matrices A into B is not same as B into A. මේ දෙක වැඩි කරාම එන උත්තරේ නෙමෙයි මේ දෙක වැඩි කරාම වෙන matrix එකක් එනවා. So therefore matrices are not fields. So field එකක් නෙමෙයි දිගට ඔක්කො කරන්න මොකද කරන්න ඕන? ඔය field වල තියෙන මොකක් හරි property එක violate වෙනවා කියලා පෙන්නන්න. එකතු කරාම ඒ જાති එකක් මෙන්නේ නැහැ. වැඩි කරාම ඒ જાති එකක් මෙන්නේ නැහැ. නැත්නම් මෙයාට additive inverse additive identity එකක් නැහැ. multiplicative identity එකක් නැහැ. නැත්නම් additive inverse එකක් නැහැ. multiplicative inverse එකක් නැහැ කියලා. එහෙම නැත්නම් මේ commutative property එක වැඩ කරන්නේ නැහැ මේ මෙයාට. multiplicative එක addition එකේ අන්න එහෙම මොකක් හරි property එක violate කරනවා කියලා පෙන්නනකො බං එයා field එකක්. field එකක්. So matrices are not fields. Integers are not fields. Okay. Right. So now we move the vector space or linear space. So now we have discussed what is a field is. And you know that integer is not a field. Matrices are not fields. But most of the other numbers are fields, even complex numbers. But not integers. Right. So this is how you define vector space. Okay. මේවල vectors නෙමෙයි vector space කියන abstract concept එක. Okay. This is the definition. So we are going to subdivide two concepts, vectors, scalars. Okay. දැන් මෙතන හිතන්න බෑ vectors කියන්නේ direction එකක් තියෙන දේවල් කියලා නෑ. හරි? ඒව කතන්දරයක් නෙමෙයි දැන් කියන්නේ. ඒ physics. ඒ තමයි ඔයගොල්ලෝ පරණ syllabus එකේ කරපු vectors. Right. Now let's define what is vector space. Now remember we have concept called scalars. We have concept called vectors. Okay, we are going to subdivide entities into scalars and vectors. Okay. So how do you know whether it's a vector? When you add two vectors, you must get a vector. Okay. When you add two vectors, you must get a vector. That is property number one. Okay, satisfied not. Right. For example, if you take integers, when you add two integers, you get integer. You can integer කියන එක දැනට මේක satisfy කරලා තියෙන්නේ. Okay. Matrices satisfy this, has satisfied this, right? When you add two matrices, you get a matrix. Right. So again, මේ පළවෙනි property එක satisfy කරන ගොඩක් දේවල් තියෙනවා. කියන්නේ ඕන real number එකක් මේක satisfy කරනවා. Matrices satisfy කරනවා. Then what about the second property? When a vector is multiplied by a scalar, it results in a vector. ඔය කියන જાතිය vector එකක් නම් එයාව scale එකකින් කියන්නේ නිකන් number එකකින් වැඩි කරාම vector එකක්ම එනවා. ඔන්න ඔය property දෙක විතරයි වෙන්න ඕන. වෙනමුකුත් වෙන්න ඕනේ. උදාහරණයකට මේකේ කියන්නේ අපිට vector දෙකක් වැඩි කරාම vector එකක් එන්න ඕන කියලා. එහෙම කිව්ව මොකේද? Fields වල. If it is a field, when you multiply two fields, you must get a same field. But in vector, that property is not there. That property is not there. So that property is relaxed. Rather than saying when you multiply two vectors, you get a vector, it says when you multiply vector by a scalar, you must get a vector. දැන් තේරෙනවද මේ vector එකේ field එකයි වෙනසක් තියෙනවද? අපි මේ කතා කරන්නේ vector space කියන concept. right. ඇත්තටම මෙතන කරලා තියෙන්නේ relax කරලා තියෙනවා සමහර properties. එතකොට අර field වලට අහු වෙන්නේ නැති සමහර ඒවා vector එකට අහු වෙනවා දැන්. And of course other properties of vector space like u plus v plus w is u plus v plus w, associative. U plus v is same as v plus u, commutative. Okay. So these are other properties that satisfy by vectors. Identity is available, additive identity and additive inverse. But there's no multiplicative identity and multiplicative inverse. So, කෑලි අඩුයි මෙතන දැන්. For vector space, you must have additive identity and additive inverse, but there is no need for multiplicative identity and multiplicative inverse. ඔය වැඩි කිරීම කියන කතන්දරේ රිලැක්ස් කරලා තියෙන වෙක්ටර්ස් වලට එනකොට. ස්කේලර් වලට ඒක ස්ට්‍රික්ට්ලි බැලුවා අපි. වෙක්ටර්ස් වලට ඒව බලන්නේ නැහැ. ඒවා සැටිස් නොවුනත් එතකොට අපි ගන්න වෙක්ටර් පැත්තට ගන්නවා මේ ඒ දෙක තුන ඇර අනිත් ටික සැටිස් කරනවා. Okay. So distributive property must be satisfied by vectors. Associative, commutative, distributive ඒ ඔක්කොම satisfy කරනවා. හැබැයි අර multiplicative identity එකක් තියෙන්න ඕනේ නැහැ. multiplicative inverse එකක් තියෙන්න ඕනේ නැහැ. අනිත් එක vector දෙකක් වැඩි කරාම vector එකක් එන්න ඕනේ කියලා හිතෙත් නැහැ. හරි. Right. So these are some examples for vector spaces. Real coordinates are vector space. ඔය R2 කියලා ලියලා තියාගේ notes වල ඒ තියෙන Euclidean space එක නැත්නම් කණ්ඩාංග තලය. Polynomials are vector spaces. So when you add two polynomials, you get a polynomial. When you multiply polynomial by polynomial, කියන්නේ ax squared plus bx plus c වගේ ගාන පද හතරේ බලය ඕන ගානක් දාලා ලියන එක. Functions are vectors, vector spaces. Matrices, on the matrices then ahuna. Because when you multiply, when you add two matrices, it's a matrix. Okay. And there's a additive inverse matrix. They can have inverse killer. So matrices are not fields, but matrices are vectors. I matrices field no any කියලා explain කරන්නේ නේද? හැබැයි vector වෙනවා. මොකද vector එක matrix එකක් scale එකකින් නැත්නම් 5 වගේ number එකකින් වැඩි කරාම ආයි matrix එකම වෙනවා. මොකද මේ vectors වල තියෙන මේ property එක scale එකකින් වැඩි කරාම vector එකක් එන්න ඕනේ කියලා විතරයි කියන්නේ. vector දෙකක් වැඩි කරාම vector එකක් එන්න ඕනේ කියලා කියන්නේ. And we know that when you multiply matrix by constant, you get a matrix. So these are some examples for vector spaces. And these are some examples which are not vectors. Natural numbers are not vectors. Integers are not vectors. Okay. Why natural numbers are not vectors? Because there's no additive inverse. Additive inverse is natural number. Natural number ke additive inverse is natural numbers නෙමෙයි. ඇයි ඒ? What is the additive inverse of +2? -2. ඉතින් -2 කියන්නේ natural number නෙමෙයි. ඒ additive inverse එක මේ જાතියෙම එනවා. So therefore natural numbers are not vectors. Right. So these are some examples they have given. මේ කෙලිම UCSC note එක ගන්න තියෙනවා. මේ මෙතන කියන්නේ addition operation එක. Multiplication. Okay. So complex real numbers are vectors. Real numbers are vector කියන property එක satisfy කරනවා. Complex numbers satisfy කරනවා. Integer satisfy නොකරට මොකෝ හරි complex numbers පවා satisfy කරනවා. ඒවා complex number එක කියන්නේ මොකද්ද කියලා explain කරනකොට යාගේ note එකේ complex numbers ගැන කතා කරලා තියෙනවා. Right, Euclidean space is a vector. Now I am into your note, okay? Euclidean space එකේ තියෙන මොකද coordinates? X, y coordinates. So then there's something called unitary space, which is related to complex vectors. So you can complex numbers or vectors, sorry. And that is also vector. Because when you add such things, you get a same thing, type of things. Matrices are vectors. Matrix එක එකතු කරාම වෙන්නේ මොකද්ද? මේ ඔප්පු කරන්න කියලා කියන්න පුළුවන්. මේ එකතු කරලා පෙන්නන්න ඕන. මේ ඇවිල්ලා තියෙන matrix එකම තමයි කියන්නේ. When you multiply matrix by a constant scalar, you get a matrix. ඔප්පු කරන්නකොත් මේක ලියන්න තියෙන්නේ. matrix එකක් එකතු කරලා පෙන්නන්න මේ matrix එක. by definition of how to add matrices. මොකද matrix add කරන definition නැත්නම් ඒ definition එක දැම්මට පස්සේ වටින matrix එක. When you multiply matrix by scalar constant, you get a matrix. Yes, vector space. Matrices are in vectors. Okay. All polynomials කියන්නේ 3x ඝනය ධන 4x වර්ගය ධන 5x ධන 8 වගේ ඕන x පදයක් තියෙන පුළුවන්. x ඝන පද 4 පද 5 පද 6 පද. Right. So when we call it polynomials, so this is how we write it in general format, right? A0 plus A1x plus A2x squared plus A3x cubed plus A4x to the power 4 plus ANx to the power n. මෙන්න මෙහෙම ලියන polynomials with vector space. Because when you add two polynomials, you get a polynomial. When you multiply a polynomial by constant like k, එතකොට හැමතිස්සෙම ka0 plus ka1x, ka2x, that is also polynomial. ඊට පස්සේ බලන්න අර තියෙන properties, cumulative property ඔක්කොම satisfy වෙන polynomials වල. Okay. So their polynomials are vectors. ඔප්පු කරන්න කිව්වොත් එම් polynomial දෙක එකතු කරාම vector එකක් මේ polynomial එකක් වෙනවා කියලා පෙන්නනවා. මොකද මේ වෙන වෙනම constant එකතු කරනවා. ආයිත් ඒවට polynomial format එක ගන්න. මේවා question විදිහට එන්න පුළුවන්. හරි polynomial එකක් vector space කියලා ඔප්පු කරන්න. එතකොට එකතු කරාම ඉන්නේ මේ polynomial එකක්ම කියලා පෙන්නන්න ඕනේ. මේ තියෙන polynomial නැත්නම් constant එකක්. constant වාරයක් x පදයක්, constant වාරයක් x වර්ග පදයක්. When you multiply polynomial by constant, you get a polynomial because just the constant coefficients are changed. සමහරවිට මේ වර ඕනටත් වැඩිය ලේසි. හරි. හැබැයි සබ්ජෙක්ට් එකට ඔළුව මූණ දෙන්න පොඩ්ඩක් බය හිතෙනවා. මොකද මේ notation උයි අර ඔය මේවා එක තියෙනවා. Right. So remember we can do the addition. And when you add, you must get a vector. And also it's x plus y is same as y plus x. එකතු කරද්දී කොයි එක දිස්සා තියෙන කෙනෙක් වැදගත් නැහැ vector එකට. And of course the distribution law, additive inverse is there. This is properties related to multiply by scalar. When you multiply by scalar, you must get the same vector. Okay. ඔන්න ඔතර ඔක ගිය අවුරුද්දේ පේපර් එකේ අහලා තියෙන්නේ මෙන්න මේක ඔප්පු කරන්න. That means you need to prove that for vector, when you add a zero vector, you get the same vector. Okay. ඒක prove කරන විදිහ ටිකක් අර abstract ඉතින් හරි අර නිකන් මේ එක rule එකක් අරගෙන අනිත් rule එක වෙන්නව වැඩ කරන්න ඉතින් හරි. ඒක දැන් abstract මේ concept එක කියලා හරි. Some more results of vector space. right මට ඉතුරු note එක ඉතුරු ටික හදාගන්න වෙලාවක් හම්බුනේ නැහැ. හරි ඉතුරු ටික ඔයගොල්ලෝ පොඩ්ඩක් තනියෙන් study කරන්න පුළුවන් ප්‍රමාණයකට. පුළුවන් ප්‍රමාණයකට. හරි. Because this will be your last topic, last class. Okay. Right. I hope you learned something, right, from the math topics. Of course, other topics we have finished. Again, you have a lot of responsibilities when it comes to system and network administration subject. You have, make sure you read the reference book, okay, because now your exams are nearing. Make sure you read the reference book, okay. And also management and entrepreneurship also, if possible, read the reference book, okay. But security subject, information system security, mostly you can survive with the notes. And maybe you can refer to the UCSC, refer to the reference book as well, okay. Professional practice, I think it is the easier question, easy paper. Only thing is you need a lot of common sense and common touch with industry, right? How the professionals behaves, how the organization work and so on. Okay, right. So we'll stop at this point, right? So do your best, right? Because I never say all good luck, because you must not rely on luck. Do your best. Be a realistic person. Improve your confidence. Improve your logical thinking, right? Your character, face challenges, and do your best. Okay, right. We stop at this point.